Let's get started with lecture 23. As I said, this topic is typically a little difficult when we start manipulating some simulation diagrams, but you will see that with some practice, it's not that bad. So the idea is to simplify these block diagrams and find the equivalent transfer function between the input and the output. The way we have done so far was that I provided the equations, and then from the equations we had the block diagram. Now let's do the opposite. Giving a block diagram, what is the overall transfer function? We actually did that for some very simple block diagrams where we simply had one feedback loop. The task there is relatively simple, but what if we get something like this, where we have multiple block diagrams interconnected? They represent a system. In this case here is the system that regulates the heart rate. And if each of these blocks is a transfer function, what is the overall transfer function of the system? That's what we're going to try to answer. So as I said, the way we've been approaching this is that the equations are provided, we create a block diagram. Now let's take that one step further. And given the block diagram, the simulation diagram, how do we go back to one transfer function between the input and the output? So let me just give you a quick review of block simplification diagrams. At this point, this is trivial to you, but the idea is that each block represents a function in the system, a transfer function that gives the relation between an input and the output in the system. In this example here, we have the relation between the input voltage and the position of a DC motor. We apply the voltage, we observe the output, which is the position, and what is in the middle, that is a transfer function. We can also have systems with multiple inputs and multiple outputs. For system with multiple inputs, we can evaluate one at a time. And because you're dealing with a linear time invariant system, you can simply add the effect of each individual input to the outputs to find the overall response. So we saw some basic ways to build the simulation diagrams. These are the basic functions we covered before. The first one is a transfer function, and from this we know that the output y is g times x. For the second one is simply, again, we know that the output here is alpha times x. So the first one is a block because it's a function of s. The second one here is a triangle because to indicate that it's only a function of a constant. There is not a function of s, it's not a transfer function. The third one, if you call the output here z, would be z equals to y plus x. And if we put a negative sign here, then this would be z equals to x minus y. Right, basic stuff. We covered this before. Nothing new here. So let's move on. So now let's start looking at the basic operations that we can use to simplify the block diagrams. The first one, we use this many times, is to combine blocks in cascade. So here we have two transfer functions along the same line, g and h. The input is x. We pass that through the first transfer function, then the second transfer function. And we know at this point that the output here, y, is simply x times g times h. G and h are functions of s, just omitting it here for simplicity. Which means that these two blocks can simply be combined, and we could write g times h into one block. And again, the output is x times g times h. So we maintain the same signal in the system. Right? Anytime we have these blocks in cascade, we can simply multiply them together, and we can verify that the output does not change. The second operation you're going to see today is to move a peak-off point ahead and after a block. Let's consider this example. We have a transfer function h of s, input is x, and output is y. And we want the signal y for another part of the block that requires it. Remember the state space models where we had to find a variable somewhere? Well, this could be that. We need the variable x, and we are picking the variable f off at this specific point. The variable y at this specific point. But what if we want that range to be free? We have, for example, another block here, and we want to combine these two blocks, we cannot pick the point, we cannot pick the signal y where is indicated there. We could instead do it in front of the block, ahead of the block. But if there is the case, then what do we have to do? Well, the signal here that we are picking is indeed x times h. So if we decide to pick the signal at this point instead, to have the same output, we would need to add this block, h of s, such that the signal that is coming out of all this operation is the same, is still h times x. So these two systems are precisely the same. The only difference is the second one would require this additional block to maintain the signal y exactly the same. The difference is that we took this point, moved it ahead. And by moving it ahead, now we need to add the function h of s in the line of y, such that the signal y does not change. It's h times x in both cases. And you may again say, why are we doing this? It's just adding more complications. Well, if we had another function here, let's say a function p, now we would be able to simplify them, put them together in one block. Whereas here, we cannot, because we need access to the intermediate signal y. Right? So if you want to get a signal, that a peak-off point, move that away, you need to manipulate the simulation diagram accordingly. Okay, any questions here? No? All right.
Sorry, just can you repeat what you said about, you said we can't do something. Can you just repeat that part?
If we had a function here, function p, we cannot simply combine p and h in the same block now.
Oh, got it. Thanks.
Right? Because if we do that, then we lose the signal that is we need for something else. Well, that's the advantage of then moving the peak-off point somewhere else. Now let's look at a summing point. The idea is still the same. We want to free some signals. We want to manipulate the system in a different way, such that simplifications can happen. And it turns out that for that, we will have, for example, here to move this sum. This sum is inconvenient there. We want that to go somewhere else. So if you want to move this sum over there, what do we have to do? Well, let's look at the signal y. What is y? Y is x plus z times h. And what is the signal in this new configuration here, where the sum goes to the other side? We have y equals to h of s times x plus z times something, whatever goes in that box. What needs to go in that box to make the signal the same as in the previous case?
H of s.
H of s, very good. So we need to add h of s here. We can now factor out h of s, and this becomes x plus z, which is the same we had before. So when you move the peak-off point ahead, we have to create this additional block that now multiplies it by h of s. If you're not sure about the operation, should I multiply, should I divide? Well, just try to calculate the signal in both cases and make sure that the signal remains the same. Now let's do the opposite. We have a peak-off point that is behind the block, and you want to move ahead of the block, you want to move that behind the block. What is the output here? Let me call this output W. And what is W? W is x times h of s plus z. The x times h of s is y. It's the same there. If you now move the peak-off point behind the block, what is the new transfer function? Is y equals to x plus z times something that goes in that box, all times h of s. So what needs to go in the box such that the transfer function does not change?
1 over h of s.
Very good. 1 over h of s. If that is the case, we can put 1 over h of s here, And now we can see that when you multiply this out, we have x h of s plus z. And we go back to the original function. So the signal w, which in this case would be at this point here, does not change. Any questions here? No? Okay. So do you see that every time I'm doing this little operation, I create a signal at one specific point, I calculate the equation for that signal, and then I verify the result of my operation to make sure that the point specifically at that signal after manipulating the blocks remains exactly the same. All right? So if you're not sure about whether you should divide, multiply, add, subtract, whatever, always create the equation, and the equation will tell you if you did the right thing or not. So let's move on to the last two operations we need. We covered them already, but let's do them again here just to summarize. And they have the full package that will allow us to do some examples. One of the most important ones is to eliminate the feedback loop. And in this case, when you have h of s, what would be the equivalent transfer function if we eliminate the feedback loop in this other, this is the simplified version here? We covered this before. The equivalent transfer function would be does this ring a bell? 1 over 1, excuse me, h of s divided by 1 plus h of s. We can find this easily. We can write an expression for y. Y is x minus y, which is this signal right there, x minus y, all times h of s. You can factor all y's on this side of the equation. So we have y1 plus h of s equals to x h of s, and then y over x is h of s divided by 1 plus h of s. All right, so this is the equivalent. We're writing it that way. Now you notice here a negative sign. If we make this negative sign positive, then this becomes negative. All right, so this would be positive, and this would become negative, negative, negative. Now we covered this one before. Okay. Last one is when we have a feedback loop, but now there is a line function in the feed. There's a line function and there is a feedback function in this case g of s. What is the closed loop transfer function here? Is h of s. We did this one before. 1 plus h of s times g of s. And once again, we can calculate this if we want. Just create the signal here. What is the signal there? Well, that's y equals to x minus y times g of s, all times h of s. All right, this part here in parentheses is the signal there. Multiply that by h of s, that gives y. And now we have y, if you put all y's to the left side, 1 plus g of s h of s equals to x h of s, which means that y over x is h of s divided by 1 plus g of s h of s. And once again, if we flip this negative sign to make it a positive sign, then this signal down there becomes negative. I can follow the reasoning with a positive sign, and that's what we get. Okay, so that's the last operation we need. Now we have all the operations to be able to simplify block diagrams. Before we do an example, are there any questions?
Yeah, sorry, could you just quickly go back to that previous eliminating a feedback loop slide?
Yeah.
Okay, perfect, thank you.
These last two here are not new. We covered them before. All right, so that's why I'm going through them fast. Okay. Any other questions? No? All right. So what is the transfer function, the closed loop transfer function of this block diagram? This one is simple. It only has a line function and it has a feedback function. So this entire line function here can be simplified because it's always in cascade here in series. We can simplify this to C times A times G. I'm going to omit the S just to make things easy. And then we have now a line function and a feedback function. Our output y over transfer function y over x is the line function itself, so C times A times G, divided by 1 plus the line function C times A times G times the feedback function H. All right, so this is our H of S. H of S. And our H here is what we call the G of S in this example here. All right, that's the closed loop transfer function, and pay attention to the positive sign here because it's a negative feedback loop. All right. Easy, right? Let me know if you have questions. You can slow down. Now let's do this one. This is a DC motor, is a feedback loop for a DC motor. There is no controller here. This is how it works. It's the inherent feedback that it has to regulate the voltage. What is the transfer function between theta and V? Theta is the position, V is the input voltage. So if you want position over input voltage, then let's set the other input to 0 for now. And what do we do here? What can we do? If that sum goes away, it goes to 0, then all these three blocks here can be combined into one. That would be our function H of S in that feedback loop. And then in the feedback loop here, we have G of S. We have another function that feeds back to the sum. So what is the transfer function? Let's look at this point first. If you just do the transfer function up to that point, we can eliminate this feedback loop first. And that would be now the multiplication of all these functions times Ki times 1 over Js plus B, all divided by 1 plus that, but now times Km, which is the feedback function. And so this gives now the transfer function of this part of the system. We still have this block 1 over S that is now in cascade with this entire function. So we can now simply multiply this by 1 over S. And this gives us the entire transfer function theta over V of S.
Sorry, so if at the beginning we have a sum, we just write 1 over 1 minus the same thing, and if we have a minus, we write like
Plus.
Oh, okay, got it. Thanks. Yeah.
You can, you don't need to memorize these things. You can look through the derivation here, and it would be obvious that if this is now positive, then when you send that signal to the other side, it becomes negative, which will create a negative sign down here. Okay, any questions here? Are we good with this? Can I continue this part? Is this clear? Yeah, if I hear nothing, I'm assuming that everything is fine.
Sure, Professor.
Yeah.
Like if you can see the derivation again for the positive, when it's positive and when it's negative.
For which part?
Like slide 9 and 10, can I just quickly see them again?
For the positive and in negative.
Yeah, for the transfer.
These ones here?
Yeah. So when it's negative, it's 1 plus like G of S and H of S.
Yeah, so let's do this again. So you see that where is this negative sign showing up? It's showing up right there, right? It's showing up right there. If that was positive, it was a positive, we would have X plus YG times H. When I move now this multiplication to the other side of the equation, we have Y minus YGH equals to XH. Now we can factor out Y. 1 minus GH equals to XH, which means that Y over X is H over 1 minus GH. Okay. And notice that when H is 1, then G is 1, then we simply have this goes to 1, and then we go back to this example. Okay. All right, so let's continue here. Now that we have this the form for this transfer function, we can try to simplify this. And the way you're going to simplify this is by finding the common denominator in the denominator of the transfer function. So we have ki in the top there, gs plus b, all divided by, now we find the common denominator, which happens to be the same as the denominator of the numerator of the transfer function. We can now multiply that by 1, ls plus r, js plus b times ki. No, there's no times ki, sorry. Plus ki times km. Right, and all this times 1 over s. Right, so if we now if you see that you have two terms in the denominator, if I simplify the function there, we go back to what we had in the beginning. But now these denominators can cancel out, and the transfer function simplifies to ki over this new Apple Pencil is not great. The old one was more robust. There we go. That's the times 1 over s. Don't forget that. That's the now transfer function between the input and the output. Okay, simple math now. We just finding a common denominator and then canceling out denominator of the numerator and the denominator of that fraction. Questions? Any questions? No?
No.
No. Alrighty. If there are no questions, let's do something a little more complicated then. But I just want to make sure that this is clear before we move on. Things get a bit more complicated. No? Alrighty. So this example here, this slide here, you can skip. Is just for more like practical considerations about the DC motor. Let's do this one. This one is a bit more interesting, isn't it? Find the transfer function between the output y and the input r. This one I'm going to solve on the tablet, and then next ones we're going to go to the whiteboard. So let's look at this diagram here. We have many feedback loops connected. We have a bunch of functions, and you want to find the transfer function y over r. What can we simplify right away? Can we combine blocks? Can we eliminate the feedback loop? Is there any simplification that we can do right away without moving things around? I don't think so. There is really nothing we can do as it stands right now. All the feedback loops, we could potentially look at this feedback loop here that wants to be simplified, but there is this signal right there. So if you simplify that feedback loop, you're going to lose that signal, and that signal is needed because it goes to H2. So we cannot simplify this directly because this signal is kind of in the way. So the first manipulation that we could do is to take the signal and move that away. Now, should we move it ahead, block G3, or should we move after block G4? Which one would make the simplification easier? Should we move this point right there or right there? Oh, if you move it ahead of G3, we just shifted the problem, create a new one. If you now move this to a point after G4, then you can simplify this whole thing, this whole block, this whole feedback loop. So the first thing that you're going to do here is to take this point and move it past G4. Of course, you can't just move it like that, because that would change the signal we are sending to H2. You see that the signal we are picking to send to H2 comes just after G3. But now we took the signal and moved that past G4. So let's say if this signal here that we were sending to H2 was A, now that we move the signal from A to past G4, we are actually sending A times G4. And so we changed the signal, it went from A to A times G4. So what should we do to that signal to make it the same, to make it remain the same?
Divided by G4. Okay.
Divided by G4, exactly. So the function H2 on top here, H2 of S, we can divide that by G4 of S. So now when the signal goes through, G4s will cancel out, and you are back with the original signal, which would be the signal A picked off right after G3. Does this make sense? Does this make sense? Well, I could have just written here another block 1 over G4, right? But I'm now combining G4 and H2, so we have H2 divided by G4. Yeah?
Yeah, it makes sense.
Okay. Alrighty, so here we now have H2 divided by G4. All functions of S, of course. I'm just omitting that for now. What else we do now? Well, now that we have moved this point, this pickoff point away, we have these 3 functions that can be simplified. We have 2 operations that we could do. The first one is to combine G3 and G4 into one block. That would be simply G3 times G4. And the other operation is to eliminate the feedback loop. We have now a line function G3, G4, and you have a feedback function H1. So how would now the feedback, the simplified version of that look like? Would you have the line function G3 times G4 divided by what?
So first there is plus or minus.
1 minus, yeah, because you see the positive sign there. Very good. Minus
G3, G4 multiplied by H1.
multiplied by H1. Excellent. So G3, G4, 1 minus G3, G4, H1. Remember that in the absence of any sign here, we assume to be a positive sign because it's a positive feedback loop. Now it's 1 minus line function times the feedback function. Very well. So we simplified that too. What do we do next? What is the next operation? How can we continue our simplification?
Would you do the loop with H2 over G4S?
Very good. Would do this feedback loop, which is a feedback loop, is just going from the top, but mathematically is exactly the same as those that go from the bottom. We can now simplify this whole thing. So here is the block diagram that I just drew there. Now we can simplify this entire thing. Which one is the line function? Which one is the feedback function? Well, the line function is clearly G2 times G3 times G4 divided by 1 minus G3 G4 H1. All right? Basically multiplying these two. That's the line function. And now we divide the whole thing by what?
1 plus.
1 plus the same function?
No, yeah, this one and multiply by H2 over G4.
Times, correctly, times H2 divided by G4. Times H2 divided by G4. Okay. Yeah. Is that correct? G2, G3, G4, 1 minus G3, G4, H1. Yep, everything is good. Now we can simplify this. What can we do? Well, we can see that this G4 and this G4 will cancel out. We can find a common denominator for the denominator of the transfer function, G2, G3, G4. So the top for now doesn't change. 1 minus G3, G4, H1. And the common denominator here will be 1 minus G3, G4, H1. That multiplies 1 is 1 minus G3, G4, H1 plus G2, G3, G4, H2. So now we can cancel this and that. And you're left with G2, G3, G4 divided by 1 minus G3, G4, H1 plus G2, G3, G4, H2.
Sir,
Mm-hmm.
is there an extra G4 there? Because didn't we cancel out one of them? And the G2, G3, G4, and then cancel it out with the H2 over
Oh,
G4?
yes, correct. Yes, thank you for catching that. Yeah, this G4 has disappeared. Oh, they can still simplify all of them. Give me a second. So that G4 disappeared. Yeah, you are right. So that the other G4 remains. So G2, G3, H2. Yeah, so this G4 here is extra. Indeed. Okay. Let me just double check here to see that, make sure that I made no other mistake. So easy to make a mistake with these things. Yeah, this looks good now. Okay. Now what do we do next? What do we do next?
Combine G1 and the other.
Very good. Combine G1 in that big transfer function, and then
And we eliminate the final feedback loop.
eliminate the final feedback loop. Very good. Eliminate the final feedback loop. So this is the same transfer function I just wrote there. I forgot G. Okay, yeah. So we can now multiply G1 inside there. See, just multiply G1. That's what I have, that top function, right? Just combine the two loops. And now, now let's do the entire transfer function here. Y over S, well, Y of S over R of S is line function G1, G2, G3, G4 divided by 1 minus G3, G4, H1 plus G2, G3, H2, all divided by 1 plus the entire thing times H3 times H3. We can find now a common denominator for this mass. And the common denominator, I'm just going to do the second part here. The common denominator for this would be 1 minus G3, G4, H1 plus G2, G3, H2. It would be now that multiplies 1 plus G1, G2, G3, G4, H3. Yeah? Good? It's just the denominator part. Now we can see that the denominator becomes what I just wrote. So the denominator here and the denominator there are the same. They can cancel out. And this will simplify to G1, G2, G3, G4 divided by that whole thing there. Haha. One minus. Okay, and this is the final transfer function. Okay. Now the last step, once again, just to summarize, is that I just took the denominator because we know the numerator is not going to change. Just took the denominator here, found a common denominator. Now you see that if I divide everything by what I just multiplied there, we'll go back to the exact same function. And then once we find the common denominator, you see that the common denominator of this part will cancel out the denominator of the top of the function. And you can just combine them to find the final transfer function y over r. Okay. Are there any questions? It's not very complicated. I think the main thing, really the critical thing, is to find the very first step. Once you found the very first step, then everything falls in place. And you basically have just one operation to do at a time.
Actually, yeah, I was gonna ask, could you go back to that first step and just show how you did it again with the changing of the loop so that it would be possible to split it up?
This one, very beginning?
Yeah, yes.
Yeah. So if you look at this one, there is nothing really we can simplify right away. Right? We can, all these feedback loops have a signal that we need. So if you get rid of the blocks, you get rid of the signal, and then we are stuck. So what it could do is to take this point here and move it somewhere else. Let's say there. Why? Because once that signal is done, then this whole part here can be simplified. So if I want this signal to go away, put it somewhere else. I want to move it somewhere else. I can just eliminate the signal from here. And let's assume that the signal that I was going to send to pick off was signal A. That's the signal I need, is A, which is at that point, we're going to call the signal A. So if that is signal A, the signal here will be A times G4. Right? Originally, past the H2, what did we have? We had the signal going down here. So we would have past G2, but G3, it would past H2, we would have A times H2. Right? A would go up, would go through H2, and the output of H2 would be A times H2. But now this signal is going all the way there. And instead of feeding A to H2, we are feeding A times G4. So now becomes A times G4, and the output here will be G4 times A times H2, which is not the original signal. So to maintain this the same, we would need to take the new signal we created and multiply this new signal by 1 over G4, and then send it. All right, so now we have A times G4 that we're picking off. A times G4 goes through 1 over G4. The signal now becomes A, and then A goes through H2, and the output is A times H2, which is the same as if we picked off the point right there. These two signals now can be combined into one, and this is H2 over G4.
Makes sense. Thank you.
Yeah. Okay, so really these are the critical steps in the simplification process, is to find the first step that will lead to simplification. And once that is done, then you see that everything else, we only had one choice really. We didn't really have to think about what to do next. We only had one thing to do. Okay, and that's the entire transfer function of the system now. Are there any other questions before we move to the next exercise? No? Alrighty. So there is no other questions. Let's move on to exercise number two. In this one, you have a prosthetic hand that can be controlled to maintain a given position despite being subjected to external forces. Find the gain K1 so that the hand does not move when the desired deflection is 0 and the disturbance is T of S. So let's recap what we're doing here. We have this feedback control system that regulates the position of prosthetic hand. There is a force being applied to the hand as a disturbance, and we want the system to remain static, not to move. So when R of S is a desired input that is 0, so do not move, the desired output is 0, R of S is 0. We want the output to be 0, despite the fact that this may be subjected to disturbances. The question is, find the transfer function and calculate the gain K1 such that when there is a disturbance and the desired displacement is 0, the output is 0. That means the effect of the disturbance is not reflected in the output. How do we do that? Well, if you want to calculate the output, we need to find the transfer function. And let's find the transfer function first. So for this exercise, let's do things a little differently. Or instead of moving things around, let's see if you can just look at this block diagram and create a transfer function by just looking at it in one go. Let's look at the signal Y of S. Let's try to create an expression for Y of S without having to simplify the block diagram. What is Y of S? Let's think about all the signals that merge at this point here, multiply by G, that is Y of S. So now we need to find all the signals that come to this point here. What are the signals that we have here? We have T going here, we have R going right there, and we also have Y coming through this, going through the sum, and going back there is also being added here. In addition, we have T of S going here and there. So this point times G is Y. So all we need to do now is to find what this signal is. And this signal is a combination of this, of that, of this, and this signal. All signals that are flowing into that point. So let me write the expression for y of s, and then let's see if that makes any sense. So we have r of s minus y of s. That's the signal right here. What is the signal there? It's the same signal, but now minus k1 times t of s. All right, so r minus y minus this signal here, which is t times k1. What happens next? Everything is multiplied by k2. Everything is multiplied by k2. To the result, we add t of s. Is that a positive value? No, it's negative, so minus ts. Now we are right there. And the whole thing is multiplied by g of s. Now I'll give you a second to digest it. Does this make sense at all?
Yep.
Yeah? Let's summarize this again. So we have, let's start from r and make our way towards y. At this point, we have r minus y. Then to that signal, which if we go here, is r minus y minus the signal that is coming down here. And the signal that is coming down is t times k1. So we are there, t times k1, so minus t times k1. The entire signal, when you we move on, is multiplied by k2. So the entire signal here is multiplied by k2. As we keep going, there is another sum coming down here, and that's negative t. Then we are here. Once you take the signal multiplied by g, we have y. There it is. Yeah? We good? Any questions about this equation? No? Okay. If there are no questions about this equation, now let's try to find the transfer function. We have, let's just multiply this out first. We have y of s equals to r. I'm going to omit the s's now just for simplicity. R times k2 minus even times g of s, and multiply the whole thing. So r times k2 times g of s minus y times k2 times g of s minus k1, k2, t1, or t of s, g of s. I ended up just writing the s again. And minus t of s, g of s. Let me check my calculations here just so I don't make any mistake. Okay, so just multiplying this out. And now the question says there is going to be a disturbance, and despite the disturbance, we want the output to remain 0. We cannot set y to 0 because we can't do that. It's the output of the system. We can control the system and try to make the system go to that output, but we cannot set y to 0. We can set r to 0. We can set our desired output to 0, and hopefully it will go to 0. So if the desired input goes to 0, then this term is 0 because this is r. R of s equals to 0. So now you can factor out all y's here. y1 plus k2 g of s. I'm just moving this to the other side. Equals to negative t of s, g of s. They are common here, tg, you see, which is k1, k2 plus 1. Okay, so that's now the relation. We see the effect of the disturbance in the output. Right? Output is y, the disturbance is now our input. if we want the output to go to 0, then this whole term here goes to 0. And if this whole term goes to 0, we are left with minus Ts g of s times k1, k2 plus 1. This is going to be 0 when k1, k2 plus 1 equals to 0. Our task is to find k1, so k1 equals to negative 1 over k2. When this is met, this condition is met, then we see that the disturbance will make the output of 0, because that's the desired output, right? Which means that the effect of the disturbance does not make it to the output.
I have a question. In the second line, you said we couldn't set y of s to 0. Why was that again?
Yeah. So we cannot set, when you do a controller and we say we want the desired output to go to 0, the only thing we have control over is the input of the system, not the output. The output is a result of the input, right? If you want to go to go on a bike at 5 kilometers an hour, you have to pedal in a way that it will make you go at 5 kilometers an hour. There is no way to set the speed of your bike at 5 kilometers an hour. You manipulate the input to go to 5 kilometers an hour, right? So if you want the output to go to, say, 5, we put 5 in here. If you want the output to go to 0, this becomes 0. The desired output is 0. We don't have control directly over the output. Now you may say, well, you are contradicting yourself, Professor, because then here you just set things to 0. It's not the same exercise. You see, here I'm saying I want the desired output to be 0. So I'm setting the controller in that way by giving the input, the desired input to 0. And in this part of the exercise, I'm saying, what do I need to do here to get 0 in the output? Despite this, right? It's a different exercise. Okay.
So if we, when we have y and like input and output, we can't set output to 0, but we have to set input to 0 first, and then we can set output to 0, right?
And then what I'm doing here is, what is the condition that it has to be met so that it goes to 0 when r is 0? Yeah.
Oh, got it. Thanks.
Professor, I have a question here.
Mm-hmm.
So in this case, we just set k1, k2 plus 1 part to 0, but why we cannot set disturbance to 0? In that case, it is also make the output to 0.
Very good question. Why can't we just set the disturbance to 0? Because the disturbance is exterior to the system. We don't have control over the disturbance. Right? If we could always set a disturbance to 0, there would be no need for control systems at all.
Oh, okay, got it.
Right? It's an external thing to the system. We don't have control over it. It will be there if we like it or not. Okay. Any questions here? No? All right. So if there are no questions, I'll keep going. Let's do exercise number 5. And then I'm going to go back to a more complicated one if we have time. But this one should be relatively simple. This is exercise number 5. And I think I put this one in our final exam, if I remember correctly. The question is, and there's another one here that came from a midterm exam. This one, skills check 1. This one, I'm sure this was in a midterm. Let's do exercise 5. We have, well, all we want to do here is to compute the transfer function y over u. I'll let you guys take a look at it and see how you would address that. So there is one mistake here that you shouldn't make. That some people will inevitably do. So let's go through that. What is the first step in this? Is there anything we can simplify already.
At the beginning, a times 1 over s.
A times 1 over s can be put together. Yeah. Can be put together in one block. Pretty good. What else can we do?
Can we simplify 1 over s and d?
1 over s and d. Is this the one? No. So let me just adjust this. It's out of range. There. What can we do first? Well, yes, we can multiply these two guys. Easy. This feedback loop can be simplified as well. What else can we do? Let's start here. Let's take this feedback loop. And let's simplify that. What is the result here? It's 1 over s divided by 1 plus 1 over s times d. Now, don't get confused here because the feedback loop is going upwards. The line function is still 1 over s, right? The feedback is d. We have 1 over s divided by, common denominator is s plus d. Cancel. Cancels 1 over s plus d. So that entire thing simplifies to 1 over s plus d. So this guy and that guy can be multiplied, and we can eliminate this entire thing here. Like that. What is the result of that operation?
It is a over s plus af.
A over s plus
Af.
af.
Oh, sorry, minus s minus af.
Right. So let's look at this thing. Is this a feedback loop, first of all? Is this a feedback loop or is this a feed forward loop?
So feed forward because it's
It is a
adding.
feed forward loop. So isn't this simply 1 over s times a plus f? Look, we have a signal here. Let's call this signal right here. It's called a b. Now this marker is not working. If this signal here is b, then what we have here on this point, we have b times s times 1 over s times a plus b times f. So we are taking b, multiplying that by a over s plus f. So the whole thing here is simply 1 over s plus a. It's not a feedback loop. It's a feed forward loop. And that was the mistake I mentioned in the beginning. Can everybody see that that's 1 over a over s plus f? Yeah? Yeah? Okay. So this simplifies to u that feeds that sum. This whole thing here simplifies to a over s plus f. This whole portion here simplifies to 1 over s plus d. Here we have b and y. And then we take the signal here, multiply that goes back with the feedback loop k. It's here. Yeah. Any questions? No? What do we do next then? What do we do next?
So we want to get rid of the feedback loop at the bottom.
We can eliminate the feedback loop. Yeah, we can simply multiply these two and eliminate the feedback loop. So let's do that. That is A over S. I'm going to take one step. We'll do this one step ahead here. If we find a common denominator for this function, we could write this as A plus Fs over S. Right, simplifying the common denominator here is A. Sorry, the common denominator is S. So there's A plus F times S. If we divide the whole thing here, we go back there. So just one step to save some time. So now we have A plus Fs divided by S times S plus D. I'm just multiplying these two. Divided by 1 plus the same thing, A plus Fs divided by S plus D times K. So this feedback loop here is this portion. Don't forget our variable B that now multiplies the result of this feedback loop. So if you multiply this whole thing by B, this is y over S, or y of S over U of S. Right? This portion is this portion here. And this will now be in cascade with B, then B moves there. With this, we can find a common denominator for this portion here. And the common denominator there is simply S plus D. So this is S plus D plus A plus Fs plus times K. Times K. So this cancels that and simplifies to A plus Fs divided by S plus D plus A plus Fs times K, all times B. Yep. Questions?
Professor, so for the transfer function, the numerator of the first transfer function that you wrote,
Did this one?
no, the one in blue.
This one?
No, y of S, yeah, the numerator. How did you get that? Because I'm getting something different. I'm getting A plus Fs times S plus D plus S all over S into bracket S plus D.
Okay, so this entire transfer function here is the line function, which is the multiplication of these two. Right, so just this multiplied by that is A plus F divided by S times S plus D. Do we agree there?
Oh yeah, that's where I made the mistake. I did the LCM instead of multiplying.
Oh, okay. Yeah. And then the denominator, so this is the top, and then the denominator is 1 plus the same thing, but then times K. Okay. Any questions? All right, so if there are no questions, let me find, let's do another exercise. Now, which one? Which one is faster to do? So we have a few minutes left. Okay, I'll leave exercise 4 for later. And there is a video solution there as well. So just leave the video for you to watch. Let's do a skills check 1. That one doesn't have a solution, so we can do that together. So let you guys think about this problem. This came from a midterm examination, from a control systems class, not from this course specifically. But we covered this topic there, so I just copied it here. And we want to find the transfer function here. So take a look at this and think about the first steps in this simplification. As I clean the whiteboard. By the way, who is coming to the lecture on Thursday? Do you have a midterm exactly at the same time, or you're studying for for the final?
It's a 24-hour thing. Like he posted at midnight, and it's due midnight.
Oh, that's good.
Yeah, but I probably won't have time to like think of questions to ask you.
Yeah.
Before, yeah.
So who is coming? Let me know in the chat there. See if maybe it's not even worth having a lecture if nobody's showing up.
Is that this Thursday, like this week or next week?
This week.
Okay.
It's last day of classes.
Could I ask what course is that exam for?
Dynamics of machinery.
Okay. Okay. So I think that's a mech course, right?
Yeah, it's just for like the biomed mechs. Yeah.
Okay. Then I think then all the biomed elect students will be here Thursday.
I might still like come, but like I won't be like asking questions. I'll probably just be like listening. But
all right. Well, let's have the lecture then. Anyways. Okay. Let me find the right one. Which one is this? That. No, that's the one we just did. Here it is. So yes, so let's have the lecture on Thursday. That's our final lecture. We can have a chat about the final exam as well. And now you have 24 hours to do the final. You'll be fine if you come to a 1 hour and 20-minute lecture. Right?
yep.
It's our last lecture, guys. So just show up. All right. And next semester things are it's looking like we're going back to in person. At least my class will be in person. And the next semester we got a confirmation that pretty much all classes are going to be in person.
Ours just got changed to online. Pretty much 90% of my classes.
For the winter?
Yeah.
Yeah. For the spring and the fall, I think we'll be back in person. Anyways, I'll be on campus. You're welcome to stop by the lab, take a look at what we do there when you are around. Okay, let's look at this one. What would be the first step in this process here, this simplification? Is there anything we can simplify right away? Well, there is this beautiful feedback loop here. All right, we just did this once. I'm just going to write the result. What is the result here?
1 over S over, oh.
Yeah, 1 over S. All right, let's do that. 1 over S divided by 1 plus
D over S.
D over S, yeah. Is that a B? Oh, it's a B. No, D, sorry. Yeah, D over S, which simplifies to that. Is that a negative loop? Yeah, so it's negative, hence the positive sign here, positive sign there. So once we factor out S, the denominator cancels, and then you're left with it. Once that is simplified, what do we do next? Can we eliminate this feedback loop here? For example, no, we can't because there is this sum. Can we eliminate this big feedback loop? No, because there is still this stuff here in the way. Can you multiply this function and that function? No, because there is a feedback loop here. So really, this sum is messing everything up, because if this sum wasn't there, then we would be able to simplify this feedback loop, and we would be able to continue our development. So this sum is the one causing problems. Now we need to move this away. Where can we put it? Well, we could move this sum ahead of the integrator. Ahead of the integrator. Right, so let's try to do that. So u of s that doesn't change. 1 over s plus 1. Then here we have that 1 over s. Is that a positive? This is positive. So, and this is that part. 1 over s plus d. And then we have b and y of s. And this whole thing has a feedback here. And the feedback is k, and it goes all the way in the beginning. Now we want to move this sum ahead of the block, which means that if you move the sum ahead of the block, we can simply put the sum over there. Or even create, to avoid confusion, you can create another sum here. And take this point and then feed it right there. What manipulation do we need to do in order for this signal to be injected right here instead? Let's think about it. At this point where the signal comes in the loop here, we are injecting A at this point. You see, right after the integrator, we are injecting A. Right? If you take this signal and move it here, the signal will go through the integrator, and we would be at this point adding A divided by S. If we simply do this, so this is A. If you simply put this signal there, we see that now A goes into the loop here, and at this point we were injecting simply A, but now we are injecting A over S. So what do we need to do to this block?
AS.
AS, very good. This block now needs to become A times S. And this is the key to solve the entire problem, because you see everything now is A times S. Let me recap this. If the signal is coming over here, right after the integrator, we are injecting this signal times A here. So basically we're injecting, let's say, just A. If the signal now, the sum is moved ahead of the block, we are taking A, making that go through the integrator, so we now have AS at this point. We had A, now we have AS. So by moving the pickoff point ahead of the integrator, we need to multiply A by S. So now when you go through the integrator here, it gets to the point after the integrator where we still now have A over S divided by S is A. Okay, good. What can we do next?
Sorry, can I ask a question?
Mhm.
I just don't know why we have two addition blocks between 1 over s and 1 over s plus 1.
2 additional blocks. You mean this the
Yeah,
sums?
can't we just use one?
Yeah, we can use one. Yeah, I just decided to split them to highlight that, and now we can remove this feedback loop.
Oh, got it.
What is the result here for this feedback loop? Is 1 over s divided by 1 minus 1 over s, which is 1 over s minus 1. But negative because this is a positive loop. So this becomes 1 over s minus 1. What about this guy here? This whole thing here. Is this a feedback? Is this a feed forward?
Feed forward. So it's just the as
So that
plus 1 over s plus 1.
As plus 1 over s plus 1. We can now continue our development. U of s that feeds the sum. This block becomes as plus 1 over s minus 1, plus 1, excuse me, plus 1. This thing here becomes 1 over s minus 1. Then this one doesn't change. 1 over s plus d times b whole thing times k goes there, and this is y of s. What do we do next?
Cascade add all the transfer functions and then remove the feedback.
Right. Now we are pretty much ready to go here. We can multiply all these blocks together and eliminate the feedback loop. What can we do in this case? We can maybe find the common denominator here. So as plus 1 over s plus 1 is the same as as times s plus 1 divided by s plus 1. So this can change to that, and just to make our life easier, as s plus 1 divided by s plus 1. Now we can multiply the whole thing here, then you see it's easier now. S plus 1 times s minus 1 is s squared minus 1 times s plus d. So as, I'm running out of space here, s plus 1, multiplication of all numerators divided by the multiplication of all denominators. S plus 1 times s minus 1 is s squared minus 1 times s plus d. Divided by the same thing. There is no, can't do copy and paste when doing this by hand. A1 plus the same thing, as s plus 1 divided by s squared. Oh, out of reach, minus 1 s plus d and times k. And the whole thing times b. All right, I can now simplify this, we'll post the final solution later. Basically, this denominator multiplies 1, and then everything cancels out. That's the transfer function. So the key for this exercise was really to find this manipulation here. Move this peak of this sum ahead of the block, and once we did that, everything falls in place. There's just the one way to go. Right? It's not that hard. And once again, exactly like in the very first example we did, the key was to find the first manipulation. And once that is done, everything else falls in place. Okay. All right, folks. I think that's it for today. I'll post the final solution for this one later because I'm running out of space here. But you get the steps. Now it's just simple math right there, right?